Turning to slide 101, the outline shows that we have now reached the error messages section, which is a fairly long section discussing a little bit about maximum likelihood theory and non-identification matters related to the error messages that you get from latent transition analysis in Mplus. On slide 102, I give some basic information about ML estimation. We maximize the log likelihood function by finding an estimate of a parameter that gives a 0 first-order derivative and a negative second-order derivative. So here you have an example. X-axis is the parameter that varies, and we want to find a particular value that we'll call an estimate. On the y-axis, we have the log likelihood, and we're saying that we want the estimate to be the value of the parameter that gives the highest log likelihood, that is the peak up here. We find that peak iteratively. For instance, we may have a starting value down here, and where we see that we have a positive improvement in the log likelihood, the positive slope with respect to the parameter, and therefore should move to the right to get to the peak, where the first-order derivative becomes 0. If we go too far, the first-order derivative becomes negative, and we will go back that way. Well, we want to make sure that this is actually a peak and not a valley, and to do that, we want to find a negative second-order derivative. This is a case of a peaked log likelihood, which corresponds to a small standard error. That is a well-determined estimate. In contrast, you have the picture on the right, where you have a very flat log likelihood in a large part of the parameter space. So you would get a large standard error, or if this is totally flat, it's a non-identified model, because you have two different parameter values that give the same log likelihood value, so you can't tell which one to choose. Non-identified model. Now, the real-world situation here is more complex. We have a bumpy log likelihood, which is known to be the case when you have mixtures. So you have several local maxima here, so you bump up and down, and you want to find the highest peak, not a local peak. So you use many starts. We discuss that more in short course topic 5 on the Mplus website and show pictures of the log likelihood in slide 116. And not only that, but we have to search for the best estimate in many dimensions. Not only for one parameter, but like for output 12, we would have 63 parameters. So you look for the maximum with respect to 63 different dimensions. That's pretty amazing that this actually works. Turning to slide 103, we want to introduce a key concept of the information matrix. So the ML estimate of the parameter vector theta, say that you have 63 parameters. That parameter estimate has a covariance matrix V of that theta hat, the estimated. That's the I to the power of -1, that is inverted information matrix I. On the diagonal, if you take the square root of them, you get the standard errors. Tech 3 gives this covariance matrix and the corresponding correlation matrix. Now, the information matrix can be approximated, can be estimated in at least 3 different ways. In Mplus, we do it by using first-order derivative products, using the MLF estimator, or using a negative second-order derivative matrix, which is the ML estimator, sometimes the expected second-order derivative matrix, or a sandwich combining the two, which is MLR. That is, you have as bread of the sandwich MLF component, and as the meat of the sandwich, the ML component. Now, the information matrix has to be positive definite, which means that it has to be greater than 0 in the single parameter case. Positive definite, greater than 0 in the single parameter case. The more peaked the log likelihood is, the smaller the parameter estimate and the standard error. That is, the better determined the estimate is, like in the figure A on the previous slide. And when the log likelihood is flat, the second order derivative is 0. So it's not positive, it's not negative, but it's 0. And therefore the parameter is not identified. Or another way to say that is that the model is not identified if two sets of parameter values give the same log likelihood value. That means that you can get different estimates, but they give the same log likelihood, so you can't tell the estimates apart using the maximum likelihood principle. There's also a concept of empirical non-identification. That's for models that are identified in principle, but in certain data sets you don't have enough information to identify at least one parameter. On slide 104 then, we connect up with non-identified models using the concept of the information matrix. A non-identified model has a singular information matrix. Singular means in the single parameter case that it's 0. You know, we wanted it to be positive, but sometimes it is 0. And because the information matrix needs to be inverted, that is 1 divided by I in the single parameter case, it can't be singular because you can't divide by 0. And you see here in this little formula why, because the information matrix, the more information you have, the smaller this value is, which has to do with the variance and the standard error of the estimate. So the more information, the smaller the standard error. Now, technically speaking, a singular matrix has at least one zero eigenvalue. Eigenvalues and eigenvectors are a way to characterize a matrix. So this idea of eigenvalues is very helpful here to numerically determine when you get too close to singularity, that is, too close to dividing by 0. And that leads us to the idea of condition number. It's a good indicator of a close to singular matrix. It's the ratio of the smallest to the largest eigenvalue. And when it's very small, in this case less than 10 to the minus 10, typically in Mplus, then we numerically determine that the matrix is singular, where 10 to the minus 10 is 1 divided by 10 multiplied 10 times. So very, very small value. During the inversion of this information matrix, or attempt to invert the information matrix, Mplus actually finds the row, that is the parameter, that triggers falling below this condition number threshold. And it prints this parameter with its parameter number that corresponds to the numbers in Tech 1. We talked about 3 ways of estimating the information matrix, and one is the first order derivative product version, and that's a particularly sensitive one, able to pick up singularity and non-identification very easily, and it's always checked in Mplus, even if you ask for MLR. All of this is described in the FAQ that we have updated recently. So let's take an example on slide 105. Simple case of a one-factor model with 3 factor loadings and 3 factor variance. We call them lambda and psi. And we know then that we have forgotten to set the metric of the factor, either by fixing the first loading or fixing the factor variance to 1. In that case, we can change the parameter values by multiplying factor variance by c, constant, and dividing the loadings by square root of c, and to get the same log likelihood. So we have a whole slew of parameter values, sets of parameters, that give the same log likelihood. So we can't determine what the estimates are from the log likelihood principle. So it's non-identified. Another way to saying that is that the log likelihood is flat in the direction of psi. For instance, all psi times c values give the same log likelihood value. So you can fix psi at any value and you get the same log likelihood. So that's an experiment you can do if you think you have a non-identified model. Fix the parameter that you suspect to not be identified, fix it, and see if you get the same log likelihood as when it was free. That means it was not identified. As an example, say that you do an RI-LTA, but you've forgotten to fix the factor variance at 1, whereas you have all the loadings free and held equal across time points. Then you're going to get this message. Standard errors of the model parameter estimates may not be trustworthy for some parameters due to a non-positive definite first-order derivative product matrix. So that's the MLF check, the sensitive one. This may be due to the starting values, but probably an indication of model non-identification, and the condition number comes into play here now. It's 0.687 to the power of minus 16. So, and then you point to which parameter it is. Parameter 6 is the factor variance, correctly pointed out. But what does this mean? For those of you not used to that notation, here's an example. 0.1 d minus 1 means 0.01, which is 10 to the minus 2, where d means double precision, working with 15 digits. So 10 to the minus 2 is 0.1 d minus 1, d minus 1. Here you have d minus 16. So very small value, certainly lower than the 10 to the minus 10 threshold that we talked about in the previous slides. So this works quite well, picking up the non-identification. Sometimes you will see the message coming out in the first order derivative setting. Sometimes you will see it as described as a singular information matrix. Both of them point to a non-identified model, and we'll see several examples of that in the coming slides.